filled the air as they witnessed the long-awaited activation of the most advanced particle accelerator, the Large Hadron Collider, constructed by the European Organization for Nuclear Research. After waiting patiently for many years, they finally saw this remarkable invention poised to transform our understanding of the universe. In September 2008, the research went live following a laborious and prolonged construction phase. However, it took the inventors of the machine several years to perfect it. Since then, the Large Hadron Collider has been instrumental in solving numerous mysteries of the universe during its various experimental phases. Despite recent developments, scientists at CERN have cause for concern. Upon ramping up the Large Hadron Collider to a brand new peak energy level, they detected something unexpected and terrifying. Subsequent investigations have led to various theories attempting to explain this phenomenon, but as of now, they have not yet been verified and remain speculative. There are many unsolved mysteries in the universe. Over the years, scientists have devoted their time to investigating in an effort to comprehend and explain some of these mysteries. These mysteries include the massive black hole found in space, said to have such extreme gravity that even light cannot escape, and what lies beneath the Bermuda Triangle, also known as the Devil's Triangle. It is well known for the baffling disappearance of more than 50 ships and 20 aircraft, but these remain unanswered due to limitations in technology in the early 20th century. Physicists sought new approaches to explore the fundamental building blocks of matter. In 1931, physicist John Douglas Cockcroft and engineer Ernest Walton constructed the first operational particle accelerator. These particle accelerators are essential instruments for examining the fundamental constituents of matter. By propelling particles to extremely high energies and colliding them, scientists can study the resulting interactions and probe the fundamental forces and particles that constitute the universe. In light of how useful particle accelerators can be in explaining the mysteries of the universe, CERN built the world's largest particle accelerator. However, scientists have just discovered the terrifying fact that this particle accelerator might cause the Mandela effect because of its ability to alter the fabric of space and time. What implications does this discovery have? Many people are unsure why they remember things differently from how they actually occurred, a phenomenon known as the Mandela effect. The term was coined in 2009 by Fiona Broome, who found out that she and many others wrongly believed Nelson Mandela had passed away in the 1980s when he actually died in 2013. This effect may be caused by a number of factors, such as false memories and the strong influence of social media and the internet. However, some researchers have raised concerns that prior power-ups of the LHC may have also caused the Mandela effect. Before dismissing this discovery as a conspiracy theory, note that a number of well-known scientists and other notable figures have raised concerns. Stephen Hawking was one of the first to convey his concerns regarding the impact of the Large Hadron Collider. He warned in an interview that the collider could produce black holes that might pose a threat to the universe. Another scientist, Carlo Rovelli, expressed concerns in a blog post, suggesting that the LHC might create hypothetical strange particles that could alter their environment into something new. Figures outside the realm of science have also discussed the potential dangers associated with the Hadron Collider. Astrophysicist Carl Sagan and science fiction writer Arthur C. Clarke expressed concerns regarding the collider, suggesting it could create strangelets or even a black hole that might swallow the Earth. Even President Obama expressed worries regarding the collider causing a catastrophic event that could impact time and space. The fact that a number of significant groups, scientists, writers, and public figures have expressed unease about the LHC demonstrates how serious these concerns are. While we can't predict the consequences, we must carefully consider the potential risks and make decisions regarding the operation of the collider. Is CERN's LHC capable of resulting in the Mandela effect, as well as other impacts on our universe? The Large Hadron Collider is currently the biggest and most effective particle accelerator in the world. It was created between 1998 and 2008 in collaboration with over 10,000 scientists across more than 100 countries. It started operating on September 10, 2008, as a component of CERN's accelerator complex. The objective of this particle accelerator is to allow physicists to test the predictions of different particle theories, including measuring the characteristics of the Higgs boson, searching for the large family of new particles predicted by supersymmetric theories, and studying additional unanswered questions in particle physics. The collider is a 27-kilometer circle made of strong magnets and structures that accelerate particles to gain more energy. Inside the accelerator, two beams of high-energy particles move at an incredible speed, almost as fast as light, before they are directed to collide. These beams travel in opposite directions through separate tubes called beam pipes, which are kept at extremely low pressure. The beam pipes then follow a circular path around the accelerator due to a powerful magnetic field generated by superconducting electromagnets. These magnets are made of coils of special electric cables that operate in a state of superconductivity, allowing electricity to flow without resistance or energy loss. To maintain the magnets in the superconducting state, they require cooling to a temperature of minus 171.5 degrees Celsius, lower than that of outer space. A liquid helium system is utilized to cool the magnets and provide additional services for air supply. While the accelerator is moving at an energy of 6.5 TeV teraelectron volts per proton, protons in the LHC are accelerated from 450 GeV gigaelectron volts to 6.5 TeV. During this process, the magnetic field of the superconducting dipole magnets increases from 0.54 to 7.7 teslas. The collision energy of the protons reaches a remarkable 13 TeV. With this level of energy, the Lorentz factor that the protons achieve is about 6,930, traveling at a speed of approximately 0.9999990 times the speed of light. The time needed for a proton to complete a full orbit of the main ring is less than 90 microseconds, resulting in an incredible 11,245 revolutions per second. The journey of protons in the LHC begins in a linear particle accelerator, LINAC-4, which generates negative hydrogen ions at 160 MeV megaelectron volts. These ions then move through the proton synchrotron booster, where electrons are stripped, leaving only the nucleus with one proton. After this, the protons are accelerated to GeV and enter the proton synchrotron, reaching an energy of 26 GeV. Finally, the superproton synchrotron boosts their energy to 450 GeV before injection into the main ring. In this ring, protons are accumulated, accelerated to their peak energy over 20 minutes, and circulated for 5 to 24 hours, allowing collisions to occur at intersections. The primary focus of the LHC's physics program is proton-proton collisions, but it also has dedicated periods, typically 1 month per year, for heavy ion collisions. Lead ions are the best option for this program and are brought to an energy of 2.3 TeV per nucleon or 5.0 TeV per ion in the LHC ring. The LHC operates with a substantial amount of power and produces enormous data collections, highlighting the immense size and importance of this scientific effort. The CERN site draws approximately 100 megawatts of electrical power from the French grid during LHC operations, approximately one-third of the amount of energy used by the city of Geneva. Notably, the LHC accelerator and detectors contribute 120 megawatts to that energy demand. This is made possible by a relativistic heavy ion collider. The heavy ion program aims to examine the state of quark-gluon plasma, a state of matter believed to have existed shortly after the Big Bang, providing unique perspectives on the fundamental properties of matter and the cosmos. With the help of this particle accelerator, one of the major theories in particle physics concerning the existence of the Higgs boson particle has been proven. The Higgs boson, often known as the God particle, made its appearance in 2012 at CERN, marking a significant breakthrough in the field of particle physics. If you're wondering how the Higgs boson particle earned its nickname, it comes from a book titled The God Particle by Leon Lederman. Despite this, the moniker has encountered criticism from many physicists due to its potential to mislead the public. The Higgs boson is a subatomic particle in the standard model of physics brought about by the action of the Higgs field. The Higgs particle is a massive scalar particle with zero spin, even parity, no electric charge, and no color charge that interacts with mass. The particle is also very unstable, disintegrating into other particles almost as soon as it is produced. The Mexican hat-shaped Higgs field is an invisible force field with distinct components that are both electrically charged and neutral. The LHC locating the star's boson, as anticipated, played a crucial role. Because of the particle's importance, it helps us comprehend the reasons behind why some particles have a fundamental property that affects mass. According to how stuff works and how it works, the world's things interact together and constitute the fundamental components of matter used to make things. Researchers use boson particles, create two-particle beams, and slam them into one another really hard. A high boson is sometimes made as a component of this collision, but it does not last for a long time due to its rapid decay. Because the high boson vanishes quickly, scientists cannot directly observe it. Instead, they examine everything that was produced when it deteriorates, and as a result, they determine the decay process. If what they see matches what they expect from a Higgs boson, it suggests that a high-level boson might have been made. However, making a Higgs boson in collisions is uncommon, and numerous other collisions may appear similar. Therefore, scientists must analyze data from trillions of collisions to be sure. They require the same pattern to appear onto different detectors and examine it to verify that it isn't just random historical occurrences. Extensive scientific research has been done to check if there are connections to the Higgs field, a hypothetical field from the Big Bang proposed as an explanation for the rapid growth of space during the universe's early moments. Some theories state that a fundamental atomic field like this could be attributed to the Higgs field phenomenon. Our destiny and the nature of Earth have become the focus of exploration because, according to the standard model, there's a chance that the universe's state, known as the vacuum, might last for a long period but is not particularly stable over time. This indicates that there is a possibility that the universe's stability could change in the future, which would alter everything we have come to understand about the universe. The vast majority of high boson and top quark research focuses on determining the stability of the vacuum in which the universe exists. In the event that it is in an unstable vacuum, it could lead to important shifts in the distant future. It is necessary to accurately determine the top quark's mass by using a special kind of collider known as the electron-proton collider to determine what would ultimately happen to the universe in case the stability of the vacuum should change in the future. Scientists are also of the opinion that the Higgs field is the energy that fills up the vacuum, influencing the extreme energies of the universe's early moments. This concept suggests that the Higgs went through different changes in structure throughout the process, and over time, the forces that are visible in the universe evolved. Scientists are currently studying the connection between the Higgs field and the energy in the empty space of the universe. The energy found in space right now is very close to zero, but theories involving the Higgs field and other ideas imply that it ought to be much higher. This difference creates a big unsolved physics issue known as the cosmological constant problem. Looking back through time, we can see how physics has developed our understanding of the basic building blocks of matter and forces. In the 1960s, scientists had a tough time trying to bring together the electromagnetic and weak nuclear forces. The theories, supported by quantum field models, performed as predicted by Mill's theory that certain particles, which we knew had mass, should actually be massless. This caused a significant issue, and a theory known as Goldstone's theorem suggested the existence of particles, Goldstone bosons, which have no mass and added to the challenges. Initially, scientists paid no attention to the theory, but it eventually became extremely significant. Following Tufte and Veltman's significant progress in resolving issues with Mill's theory in the years 1971 to 72, their work, along with ideas from the renormalization group and Russian scientists, improved the theoretical basis. Even though people were initially uninterested, the theory became extremely widespread and popular, altering our perspective on particle physics. Scientists are studying the Higgs field in a variety of ways, from its potential participation in the Big Bang to how it affects the stability of the universe and how it is related to vacuum energy. Looking back at history, we see scientists are hard at work finding the secrets of the fundamental components that make up the universe. Their efforts have resulted in theories and models that help us understand the cosmos better. Quantum theories of the field, based on a notion known as gauge invariance, have done an excellent job of understanding forces like electromagnetism and the strong force. But in the early 1960s, when researchers attempted to formulate a theory that included both the weak force and gauge invariance-based electromagnetism, they ran into a lot of problems. These obstacles caused physicists to feel stuck and unable to create a complete theory for particle physics at that time. As a result, some gauge theory's excellent reputation faced issues. The problems surfaced because the predictions for the weight of the particles with weak forces, W and Z bosons, said they should have zero mass. In particle physics, mass refers to how a particle weighs when it is still. But when scientists did experiments, they found that W and Z actually have some weight, which directly contradicted additional predictions they made. Possible solutions seemed to require the presence of additional particles called Goldstone bosons. Yet, strong evidence existed implying that the alleged particles might not be real. This left physicists with a confounding question. Either gauge invariance was incorrect, or some unidentified factor gave the weak forces W and Z bosons mass without creating Goldstone bosons. By the late 1950s and early 1960s, scientists were confused about how to solve these issues and build a complete particle physics theory. Hadrons are also important in understanding how these quarks interact. When new hadrons are discovered, it gives us real-world information about how quarks behave in extreme situations. This data enhances our theoretical models. By closely studying the features and actions of these particles, scientists have identified new particles, hoping to uncover the mysteries of the strong force and gain a better comprehension of the intricate interactions between quarks and gluons. Additionally, studying hadrons at the LHC has aided scientists in growing and comprehending the prevalent model of particle physics. The standard model has been good at explaining many things, but it's not a complete theory. There are still things that it doesn't explain, such as dark matter, how fundamental forces come together, and why there's more matter than antimatter in the universe. Looking into the powerful hadron force research is an important step in being able to explain a few of the cosmos occult mysteries. Locating the Higgs boson has provided scientists with new roads to travel in particle physics, which is still being investigated to understand how it acts and what it's like, wishing to discover differences from what the standard model predicts. If they can comprehend the Higgs boson in greater detail, it might uncover things we don't know yet and advance our comprehension of physics. As scientists continue to investigate the powerful force, they believe that the data they collect will not only explain how tiny particles communicate with one another, but also lead to innovation and advancement in technology. Despite the absence of scientific fact to prove that the Large Hadron Collider caused Mandela's death or even the formation of cosmic black holes. It is important to note that while the LHC is a powerful invention that can be utilized to solve a number of cosmic mysteries and help us understand the planet we live on better, inferences of this particle accelerator in the cosmos can also have negative and irreversible impacts on our planet.